Hello everyone, my name is Shuraim and the title of my poster presentation is Monte Carlo simulation, Heisenberg and the Ising model. So what is the main difference between the Heisenberg and the Ising model? In the Ising model, the spin can orient itself into two directions, like it can be spin up and the spin down. In the Heisenberg model, a spin can orient itself in any direction. For example, a spin can be with a theta equals 30 and the phi equals 20. It can exhibit any numerical value of theta and phi. So we have considered over here the Heisenberg and the Ising model. The figure shows the Ising model picture and the Heisenberg in the XY 2D plane and the energy of each lattice site considering there is a magnetic field, external magnetic field. So the energy of each lattice site is equals to minus J, which is the interaction energy between the two lattice sites, and summation is along the neighboring sites minus B into summation of each lattice site energy. So we have used Metropolis algorithm. In the algorithm, we have to consider that whether a site will make a transition or not. In the Ising model sense, if the site has a spin up direction, will it make a transition to spin down or not? It depends upon the Metropolis criteria. The Metropolis criteria contains an alpha, which is a probability that it will make a transition from I to J or it will make a transition from J to I. Alpha is actually a Boltzmann factor. So firstly, considering that whether a site will make a transition or not, we have to find the energy of each lattice site before the transition and after the transition. And the delta E is actually a difference between the before the transition, energy of each lattice site before the transition, and energy of lattice site after the transition. If the delta E is less than 0, it will make a transition. And if it is greater than or equal to 0, then we have to take a random number. And if the and to compare it with a Boltzmann factor. If the random number is greater than Boltzmann factor, then we will keep the spin. We will keep with the previous spin configuration. If the random number is less than the Boltzmann factor, which is e to the power minus beta delta E over, and if the random number is less than Boltzmann factor, then we will update the spin configuration. It means the spin will make a transition. So following that, in the same sense as in the Heisenberg picture, we have to make a transition through changing the theta and the phi's. So what is our results and discussion? If you can see in the results and discussion section, the first curve displays the relation of internal energy with the temperature variation. As it can be seen that at low temperature, the energy is approaching to -1, indicating that all the spins are becoming aligned. At high temperature, we can see that all the spins are randomly oriented, which displays the leveling of the energy. This is an excellent agreement with the original relation in the literature. By the way, noting the factor that the first two graphs in the results and discussion is related to the Heisenberg, considering the fact that there is no external magnetic field. And in the second graph of the Heisenberg picture, the second curve is actually a magnetic order, the variation of magnetic order with the temperature. The magnetic order represents the net spin that a lattice represents at particular temperature. At low temperature, the magnetic order shows a peak, which indicates a phase transition. However, it is known that we know that phase transition does not occur in 1D model, and the reason we are getting this is that sampling rate at a low temperature is low, which causes important sampling to get stuck in the local minimum. So that is why we exceed the sampling rate at low temperature. This phase transition goes away. We have not done that because it is computationally expensive. In the third and the fourth graph, which are related to in the 2D Ising model, in the third graph, the behavior of magnetization M bar from a simulation perfectly reproduces a phase transition. From here, our estimated Curie temperature is comparable to Onsenge's calculation, despite massive fluctuations at TCS approached as the critical temperature is approached. In the case of 1D lattice, our simulation produces no discontinuity and spins fall off exponentially with the temperature, just as expected in the literature. We found at best alpha is equivalent to -2.57 and beta is equal to 0.11 and the gamma is 0.75, which are very consistent with both the mean field approximation and the Ostenger's exact solution, perhaps with the exception of alpha. In the 2D phase transition, Ostenger's critical temperature was 2.29 Kelvin, but in our case we have. So in the fourth graph, this is a relation between magnetic susceptibility versus the temperature, and considering the fact that there is no external magnetic field. So concluding my presentation, our Metropolis Carlo simulation have provided insights into Heisenberg and the Ising model, revealing how interactions between the spins govern observable properties. The Heisenberg model, with its quantum mechanical spin vectors, explains long-range order and emergent properties, while the Ising model's binary spins illuminate phase transitions and the short-range order. Simulations confirmed theoretical predictions of the phase transitions, of the symmetry breaking, emergent magnetization, and validating the simulation's accuracy. This underscores computational methods' significance in understanding intricate behaviors and their contribution to our comprehensions of quantum physics. Thank you.